remember what P was. So permutations P is the identity matrix with reordered rows. So, well, I include in reordering the possibility that you just leave them the same. So the identity matrix is okay. That's like the your basic permutation matrix. Well, your do-nothing permutation matrix is the identity. And then there are the ones that exchange 2 rows, and then the ones that exchange 3 rows, and then the ones that exchange 4. Well, it gets a little, it gets more interesting algebraically. If you've got 4 rows, you might exchange them all in one big cycle, 1 to 2, 2 to 3, 3 to 4, 4 to 1. Or you might have exchange 1 and 2 and 3 and 4. Lots of possibilities there. In fact, how many possibilities? The answer was n factorial. This is n times n minus 1 times n minus 2 times 3 times 2 times 1. That's the number of, this counts the reorderings, the possible reorderings. So it counts all the n by n permutations. And all those matrices have this nice property that they're all invertible, because we can bring those rows back into the normal order. And the matrix that does that is just the same as the transpose. You might take a permutation matrix, multiply by its transpose, and you'll see how that the ones hit the ones and give the ones in the identity matrix. So this is we'll be highly interested in matrices that have nice properties. And one property that maybe I could rewrite that as P transpose P is the identity. That tells me, in other words, that this is the inverse of that. Okay. We'll be interested in matrices that have P transpose P equal the identity. There are more of them than just permutations, but my point right now is the permutations are like a little group in the middle, in the center of these special matrices. Okay. So now we know how many there are. 24 in the case of, there are 24 4x4 permutations. There are 5 factorial, which is 120. 5 times 24 would bump us up to 120. So listing all the 5x5 permutations would be not so much fun. Okay. So that's permutations. Now also in section 2.7 is some discussion of transposes. And can I just complete that discussion? First of all, I haven't even transposed a matrix on the board here, have I? So I better do it. So suppose I take a matrix like 1, 2, 4, 3, 3, 1. So it's a rectangular matrix, 3 by 2, and I want to transpose it. So what's its I'll use a T, although MATLAB would use a prime. And the result will be, I'll write it here, because this was 3 rows and 2 columns. This was a 3 by 2 matrix. The transpose will be 2 rows and 3 columns, 2 by 3. So it's short and wider. And, of course, that column becomes a row. That column becomes the other row. And at the same time, that row became a column. This row became a column. Oh, what's the general formula for the transpose? So the transpose you see it in numbers. What I'm going to write is the same thing in symbols. The numbers are the clearest, of course. But in symbols, if I take A transpose, and I ask what number is in row I and column J of A transpose? Well, it came out of A. It came out of A by this flip across the main diagonal. And actually, it was the number in A, which was in row J, column I. So the row and column numbers just get reversed. The row number becomes the column number becomes the row number. No problem. Okay.